Okay, so we're going to talk about what is true about an original function f given the graph of its derivative. So I couldn't get to this picture, so I'm going to use this description to try to draw it. So it comes from minus infinity. It's increasing from x is negative infinity to x is negative 1.5. So it's coming up and crossing the x-axis at -3. And 1, 2, 3, 4, 5, 6. This is 6. We know that it crosses the y-axis at 6. And we know, I probably need to be able to make it higher. Rats, let's renumber this. Let's make let's go 2 at a time. Let's make this 6. Okay, so 2, 4, 6. We know that it crosses the y-axis at 6, and x-intercepts at -3, 1, and 2. And we know that it is increasing from negative infinity to negative 1.5. So that means that it's coming up here and it's sort of hitting a max or a min, but it's going to have to be a max. And then it turns over, start over. It comes up from minus infinity and goes through here. It goes up and hits a maximum, and it turns over and it passes through 6, and then it passes through 1, and it hits a minimum, and it passes through 2. Oh, it shouldn't have an inflection there. But anyway, it goes on. It's hard to draw with this. It looks something like this. And let's remember that this is the first derivative. It is not the original function. This is f prime of x. Now, here's some truths about how these all relate. If the derivative is positive, that means that the original was increasing. If the derivative is negative, that means that the original f was decreasing. And if it's 0, then that means that f is either a max or a min. Okay? So, we know those things. Now, let's start over knowing these things and draw the second derivative, or get some things known about the second derivative. Okay? So this would then become like the original function, and its derivative would be the second derivative. Now, I need to write a few truths about the second derivative. Let's do that here. So the second derivative, if it is positive, that means the original function was concave up. If the second derivative is negative, that means the original function was concave down. And if the second derivative is 0, it means you might have a point of inflection. Not guaranteed. If the concavity changes, then yes, you have a point of inflection. Otherwise, no. You have no point of inflection. Okay, so think about this. I like to draw what I call a sine line. This is going to be my second derivative. Okay. Remember, it's as if this was my original now, and I'm taking its derivative. So at a min or a max, my second derivative, well, at a minimum max, a derivative will be 0. So my second derivative is 0 here. And here's another minimum. My second derivative is 0 here, because we're taking the derivative of this. And if this would have been my original, here where it's increasing, that means that its derivative is positive. So this is all positive. If it's decreasing and I take its derivative will be negative. So it's negative in here. And here, because the function we're taking the derivative of is increasing, its derivative will be positive. Okay. So this means we have a point of inflection at x equals negative 1.5 because the concavity changes. And we have a point of inflection at x equals positive 1.5 because the concavity changed from negative to positive. Now, what we can say about the original function from the derivative, okay, the derivative is 0 here, so that means that our original f, getting this information from the derivative, when the derivative is 0, the original was either a min or a max at x equals negative 3. Our original function is either a min or a max at x equals 1. And our original function f is either a min or a max at x equals 2. That's what these zeros tell us. Okay. Now, let's see if we have enough information to, well, and let's make this a sine line while we're at it. Okay, notice if this is the sine line for the first derivative, just the first derivative, it is negative up until here, right? The pink line is below the x-axis, so it's negative here. It's positive in here, which means the original function is increasing when the derivative is positive. It's negative. It goes below the x-axis here, so the derivative is negative in here. And then it goes above the x-axis, so it's positive for the rest of time. So what this tells us is that the original, this piece right here, tells us that f is decreasing until negative 3 because the derivative is negative. It tells us right in this space that the original function is increasing because the derivative is positive. So f is, I didn't spell that right, increasing in this interval from negative 3 to 1. We have that the original function is decreasing in here from 1 to 2 because the derivative is negative. And then we have, for the rest of time, that our original function here is increasing. So we can tell all those things just from the graph of f prime. Where it's negative, the original function was decreasing. Where it's positive, the original function was increasing. Where it's 0, we had a minimum or a maximum. And then when we take the derivative of f prime, we get the derivative, we get f double prime. But when a function is increasing, its derivative is positive. So this is increasing. So its derivative is positive. Here it's decreasing. So its derivative is negative. Here it's increasing. So its derivative is positive. And we notice that we change concavity here, where this is at a max, and so its derivative is 0. Here it's at a min, so its derivative is 0. So we do change from positive to negative on the original function. So we have a point of inflection at negative 1.5, and we change from negative to positive at x equals 1.5. So we have a point of concavity here. Now, let's answer their questions. Starting here. Let's make smaller so it'll fit. Okay, so the first one. Does it have an inflection point from negative 1, which is here, to positive 1 in here? No, the inflection points are at positive 1.5 and negative 1.5 outside of there. Therefore, this answer is no, this is not true. Okay. Then, the original function f is increasing from negative 3 to 1. Didn't we just say that? Because the derivative is positive. Right here, the derivative stays positive from negative 3 to x equals 1. That means that the original function is increasing. This is a correct answer. Let's check the others, though. F has a relative maximum at negative 1.5. F prime has a relative maximum at negative 1.5, but x does not. X minimums and maximums are where the derivative is 0, so they are at negative 3, 1, and 2. So this answer is no. If this had said f prime, then it would have been true. But it is not true for plain old f. And then it says none of these are true. Well, this is incorrect because we already know that the second statement is true. So the answer is that f is increasing on the interval from x is negative 3 to x is 1. That's the true statement.